Lesson: Supervised Learning for Threat Detection. Supervised learning, a subfield of machine learning, plays a critical role in enhancing cybersecurity, particularly in the realm of threat detection. By leveraging labeled datasets to train algorithms, supervised learning models are capable of identifying and mitigating security threats with a high degree of accuracy. This lesson explores the theoretical foundations and practical applications of supervised learning in the context of cybersecurity threat detection, drawing on current research, statistics, and examples to provide a comprehensive understanding of the subject. Supervised learning involves training a machine learning model on a labeled dataset where each data point includes both input features and the corresponding output label. The objective is for the model to learn the mapping from inputs to outputs so that it can accurately predict the label for new, unseen data. In cybersecurity, these labels often represent different types of threats or normal behavior. The primary goal is to develop models that can distinguish between benign activities and malicious actions, thereby enabling proactive threat mitigation. One of the most prevalent applications of supervised learning in cybersecurity is the detection of malware. With the rapid proliferation of malware variants, traditional signature-based detection methods have become insufficient. Supervised learning models, trained on features extracted from known malware and benign software, can effectively identify new and evolving threats. For instance, research by Raff et al. Demonstrated the efficacy of deep learning models in detecting malware by analyzing byte sequences and API calls, achieving high detection rates with minimal false positives. Another critical application is intrusion detection systems, which monitor network traffic to identify potential security breaches. Supervised learning models can be trained on labeled datasets containing normal and malicious traffic patterns to detect intrusions in real time. The KDD Cup 1999 dataset, a widely used benchmark in IDS research, has facilitated the development of various supervised learning models that excel in identifying network intrusions. For example, a study by Tavalay et al. Utilized the KDD dataset to train a decision tree classifier, achieving impressive detection accuracy and demonstrating the potential of supervised learning in this domain. Phishing detection is another area where supervised learning has made significant strides. Phishing attacks, which deceive individuals into providing sensitive information, pose a severe threat to cybersecurity. Supervised learning models can be trained on features such as URL characteristics, email content, and sender information to identify phishing attempts. A notable example is the work by Bassnet et al., which employed a random forest classifier to detect phishing websites with high precision, leveraging features like domain age, presence of IP addresses in URLs, and abnormal URL lengths. The effectiveness of supervised learning in threat detection is further underscored by its ability to adapt to evolving threats. One key advantage of supervised learning models is their capacity to be retrained with new data, enabling continuous improvement in detection capabilities. As new threats emerge, labeled datasets can be updated to reflect these changes, ensuring that the models remain effective. This adaptability is crucial in the ever-changing landscape of cybersecurity, where new attack vectors and techniques are constantly being developed. Despite its advantages, supervised learning in threat detection also faces several challenges. One significant issue is the availability and quality of labeled data. Obtaining large representative datasets with accurate labels can be difficult, especially for emerging threats. Moreover, labeling data is often a labor-intensive process that requires expert knowledge. To address this challenge, researchers have explored the use of semi-supervised and active learning techniques, which combine a small amount of labeled data with a larger pool of unlabeled data to improve model performance. For example, a study by Li and Liu demonstrated the efficacy of semi-supervised learning in detecting advanced persistent threats by leveraging both labeled and unlabeled network traffic data. Another challenge is the potential for adversarial attacks, where attackers manipulate input data to deceive machine learning models. Adversarial attacks can significantly undermine the effectiveness of supervised learning models in threat detection. Researchers have developed various techniques to enhance the robustness of models against such attacks, including adversarial training, where models are trained on both clean and adversarial examples to improve their resilience. A notable study by Papernaut et al. Demonstrated that adversarial training could substantially increase the robustness of deep learning models against adversarial attacks in the context of malware detection. The interpretability of supervised learning models is also a critical consideration in cybersecurity. While complex models such as deep neural networks often achieve high accuracy, their black box nature can make it difficult to understand the reasoning behind their predictions. This lack of interpretability can be problematic in high-stakes scenarios where understanding the decision-making process is crucial. To address this issue, researchers have developed various methods to enhance model interpretability, such as feature importance analysis and the use of simpler, more transparent models like decision trees and logistic regression. For instance, the SHAP framework, introduced by Lundberg and Lee, provides a unified approach to interpreting the output of any machine learning model, enabling cybersecurity professionals to better understand and trust the predictions made by supervised learning models. The integration of supervised learning into cybersecurity infrastructure also necessitates considerations regarding computational resources and deployment. Training and deploying supervised learning models require significant computational power, particularly for complex models like deep neural networks. Additionally, real-time threat detection demands efficient algorithms that can process large volumes of data with minimal latency. Researchers have explored various optimization techniques to address these challenges, including model compression and the use of specialized hardware like GPUs and TPUs. For example, the use of model pruning and quantization techniques can reduce the computational footprint of deep learning models, making them more suitable for real-time applications in cybersecurity. The future of supervised learning in threat detection is promising, with ongoing advancements in machine learning algorithms and the increasing availability of data. Emerging techniques such as transfer learning, where models pre-trained on large datasets are fine-tuned on specific cybersecurity tasks, hold significant potential for improving detection accuracy and efficiency. Furthermore, the integration of supervised learning with other AI approaches, such as unsupervised learning and reinforcement learning, can lead to more robust and comprehensive threat detection systems. In conclusion, supervised learning has emerged as a powerful tool for enhancing cybersecurity threat detection. By leveraging labeled datasets to train models capable of identifying and mitigating threats, supervised learning offers a proactive approach to securing digital environments. Despite challenges related to data availability, adversarial attacks, and model interpretability, ongoing research and advancements in machine learning techniques continue to improve the effectiveness and robustness of supervised learning models in cybersecurity. As the threat landscape evolves, the adaptability and continuous improvement of supervised learning models will remain crucial in safeguarding against emerging cyber threats.